different way that the reason for why size designed. And I found this a very nice application, and I think he will explain us how that's work and what are the things that we can do. Thank you, Lorenzo.
Thank you, Lionel. As Lionel mentioned, I'm gonna tell you about this paper we published, I think now a year and a half ago, 2 years ago, about how to apply correlation techniques, ideally all of them, to by using a detector array, in this case, the Ariscan detector. So starting by the motivations of this is that correlation techniques give you a lot of information on different spatiotemporal scale that are also complementary with each other. So some techniques can report on, as Francesco just described, on the environment organization. Other techniques can report on the particle dynamics, so on and so forth, like oligomerization state in case of number and brightness. So however, they have their limitations. So like IMSD that was just described is the techniques that allow you to determine the diffusion modality and the environment organization at spatial scales below the resolution limit, right? However, in order to gather this information, you have to sample over a very large, a relatively large area, right? So, which is typically several times higher than the resolution limit, because you have to sample the diffusion of molecule across space. On the opposite side of this, we have FCS. So FCS doesn't really allow, it doesn't have the same potential as IMSD to assess the heterogeneity of motion within the confocal volume, but it's applied to a confocal volume. So it reports on a volume which is approximately the resolution limit. So what do we want to do? We want to get only the best, of course, of these two technologies. So we want diffusion modality determination, and we want it at the resolution limit and possibly below the resolution limit. This is our goal. So let's go take a look at how things work. So when you have a diffusion process, you have your illumination volume, and molecules go in and out of your illumination volume, giving you a sort of spike of fluorescence, which give rise to fluctuations that you can analyze through the autocorrelation function, get your FCS curve, and obtain information about the diffusion coefficient, concentration, oligomerization state. This is very nice, very straightforward in when you are in a solution. But what happens if instead of a solution, you have a diffusion through obstacles? Obstacles that may be represented by either molecular crowding or a structure, more or less complex. What you get from FCS is just a diffusion coefficient which is slower than the diffusion in water, which is expected. It's what you get in cells, but it doesn't report on what is actually happening inside your illumination volume. One technique that was mentioned in the previous talk by Francesco is spot variation FCS. So the idea of spot variation FCS is to discriminate between several kinds of common diffusion behavior that can happen in the cell. So free diffusion, impermeable obstacles, dynamic partition, and meshwork. These kinds of diffusion give rise to these different curves, which I'll show you in a minute how to obtain those. And you can see that like meshwork diffusion has a very steep slope. Microdomain has a different slope, which actually intercept in the positive values in this axis. Free diffusion intercepting 0, and so on and so forth. So you see that these curves are what? It's apparent diffusion time over a confinement parameter, which is proportional to the waist squared of your illumination volume, right? So to construct these curves, you need several illumination volumes. So if you take a very small illumination volume, say smaller than the meshwork, than the size of the mesh, then inside that volume, the molecules will largely diffuse as free diffusion, right? So you will get a point here along the free diffusion line. Increasing the volume, you will get a higher contribution of the interaction with the mesh. So you will no longer walk along the free diffusion curve, but you'll start needing more time, basically, to cross the illumination volume, right? If you increase even more the size of your volume, you will continue seeing this effect, and then you can extrapolate that you're actually walking around the meshwork with this size. If we had more points, we could actually trace this whole curve and obtain the exact shape of the structure surrounding your molecule. This is one thing. IMSD works on similar principles, but exploits the temporal dimension. So if you are in a solution, if you consider the time and how much is the broadening of the diffusion probability distribution, it will increase linearly regardless the temporal distance, right? Because there's no obstacle in this. In presence of obstacles, short times means short length, so that means that the probe is not didn't travel enough to actually interact with the structure. So you will have the same slope as free diffusion. At longer times, it will report on the time it takes for the probe to cross all this structure, and then you will have some transition in between. Per correlation function, this is a sort of summary of everything. Per correlation function tells you how the points around the points that you illuminate are connected with each other, right? So in a solution, there will be no delay between diffusion from one point to another. If you have an impenetrable obstacle, you will see connection only, in this case, in the vertical direction and not across the obstacle. If you have a barrier, here, in this case, you won't see any connection between these points and these points. You will see a slower connection between these two because it has to go around. And so this one can report on the connectivity of the surrounding and the anisotropy of the motion, like directionality and so on. If you remember from the previous lectures, all these techniques are use different instrumentation. So you can go from like single point, photon counting detectors, cameras, and so on and so forth. Because some techniques need a fine spatial sampling, other a very fast temporal sampling, and so on. So you always have to compromise. With the Eriscan, you don't have to compromise anymore. This is because it is a detector array. So it has a spatial extension, basically. And it also can acquire with a very fast acquisition speed in the order of microseconds. So you can go 1,000 times faster than the camera, still having camera capabilities. Also, the primary purpose of using the Eriscan is to use super resolution. In fact, we can actually use all of the correlation techniques that I just introduced at the super resolution scale, approximately 140 nanometers. As a fast comparison, because I don't want to go to basically, with the Eriscan, it's possible to do FCS, obtain the diffusion law at the same time in only one shot. It's possible to obtain the IMSD, PCF, and connectivity maps. Let's see how. So spot variation usually is applied by either like changing the objective using a lower numerical aperture. So it basically goes from your diffraction limit, and then you sort of increase the size of your illumination volume to get the points, get further points in your curve for the determination of the diffusion. In this case, what we are doing is we are just doing it post-processing, considering a variable number of detectors in our image. Since the detector, this is the reason why you can go in super resolution with this, is placed in place of the pinhole, it acts like a virtual pinhole that you can change post-processing. So if you take the signal coming from all the detector, it's like having a pinhole of 1.2 ARRI units. If you consider a more central area, then it will be like 0.8 ARRI units. So the point spread function will be narrower. And then you can go 0.6, and then you can go 0.2. This will give you the higher resolution, so the smaller illumination volume. You can see that the FCS curves obtained by this volume, and then smaller and smaller and smaller volume, you can see that you have the G0 increasing, meaning that you are measuring less molecules, and this is due to the shrinking of this illumination volume. So this is what we want to achieve. So we have simultaneously 4 illumination volumes from which we can extract information about the diffusion law. These are the values of the volumes we have access to, and generally these are the 3 types of environment that can hinder the diffusion. So if we have free diffusion, the interpolation, the linear interpolation of these 4 points will cross around 0. That means that it's undergoing free diffusion. If it's a meshwork, it will cross below 0. If it's a macrodomain-like, it will cross above 0. One other thing that we added is looking at the number as a function of the effective volume. This will report also on aggregation and exclusion of. So if you're looking at an area which excludes the molecules, or if it's a sort of domain in which the molecules are more. This allows us to create this 2D space in which, if we have a point in this black point, for instance, it will be a region in will mean that your probe is undergoing diffusion in microdomains and is excluded by the surroundings. So there's going to be a portion of the illumination volume which is not accessible to the probe. This is orthogonal, so you can have like meshwork with exclusion and aggregation, microdomains with exclusion and aggregation. And the farther the points are from the origin of this space, the higher is the effect. So the higher the exclusion, the higher the aggregation, the higher the confinement in these microdomains or in the mesh. IMSD can be also done across the detectors. And then it can report on diffusion, free diffusion, directed motion, confinement, and so on. Percorrelation can be done by doing the percorrelation between the central detector with the ring at a distance of approximately 50 nanometers, this other ring, another ring, another ring. Looking at how the shape of the percorrelation function is modified to assess the directionality of the molecule in that super resolution volume. Also, you can look at the percorrelation between each of the detectors that you have available. So if you consider the red detector and then this blue group of detector, or this, or this, or this, and you look at the cross correlation, the percorrelation between the black and any of these, you will get the typical curves that you are used to when you look at percolation functions. So the farther you go in space, the longer it takes for the molecule to reach them. But this, the distance of this one is subdiffraction. You are in the order of tens of nanometers, right? So you have a much higher sensitivity than that common percorrelation techniques. And also you can use all the cross correlation between the detectors to create a connectivity. So how does a connectivity map look like? This is in case of a solution. You can see that it's everything's perfectly isotropic. The diffusion has the same value in every point of the detector. The thing change as soon as you move to the cell. So let's see this data set which was acquired in the cell. And here we have the connectivity map, and here we have the anisotropy. So one thing that you can notice is that you have an area here in which the connections are slower than the rest of the region. And if you look at the anisotropy, this region corresponds to an isotropic area, whereas the surroundings, the molecules tend to avoid this region, right? So what it means that you're looking at an obstacle to diffusion at the nanometer scale in which the diffusion inside the object is relatively isotropic, and the molecules tend to flow basically around it. So specifically, this is a region of chromatin compaction that I've been analyzing, and that means that it had a region within that heterochromatin region which doesn't allow the molecules to flow. So to show you an application of this, let's look at some general cellular compartments. So what we call unstructured cytoplasm. So it's typically on the edges of the cell where there are not many organelles present. The structured cytoplasm is what you see closer to the nucleus, so where you have all the other organelles creating some sort of crowding. So you have like the mitochondria, microtubules, and everything that's usually relatively closer to the nucleus. Inside the nucleus, we have heterochromatic region, euchromatic region, and the nucleoli. So nucleoli are typically very dense, and heterochromatic regions are compacted DNA, so they should be denser than the euchromatic region, which are typically decompacted. So let's see where these points fall in our 2D plot. And you can see here that the unstructured cytoplasm show a little bit of confinement. So they all fall in the region of exclusion and microdomains, like diffusion. Right? But the unstructured cytoplasm and the structured cytoplasm have roughly the same confinement in terms of microdomains, but they have the structured cytoplasm has a higher exclusion. So meaning that the GFP, in this case, which is the program we're using, does not have access to certain organelles, which is known because they're membrane bound. So it's not complicated. You can see also from the image that you have darker region in which the probe can't diffuse it. As soon as you move to the nucleus, everything is shifted toward higher exclusion. As you can see here, these 3 points are relative to the nucleus. This is the heterochromatin. So the heterochromatin has a confinement which is relatively similar to the cytoplasm, which is also what you would get if you were measuring simply the diffusion coefficient, right? The diffusion coefficient of GFP in the nucleus and the cytoplasm is largely similar. But as soon as you move to heterochromatic region or the nucleus, you have a much stronger confinement in microdomains. So this all is telling you a nanoscale picture of what is happening inside the nucleus. And on top of this, all of this is done with minimal interference with the sample because we are not labeling anything with anything. We're just using GFP, which is an inert probe, which doesn't interact with the cellular machinery, to report on the structure of the surrounding. We can also do IMSD, and we can obtain diffusion coefficients. We can obtain length of confinement, and so on and so forth. We could, in principle, also report on oligomerization states, concentration, environment organization, connectivity, anisotropy, diffusion modality, diffusion coefficient, all in one single point measurement of approximately 30 seconds. So this has been published exactly like a couple of years ago. Now what we'll be doing next is create another microscope which relies on another detector to include also single photon counting detection and lifetime measurements or hyperspectral capabilities. And that's it.